to ask yourself two questions before you can answer how big a sample you need. The first question you got to ask yourself is, number one, how confident do you want to be? How confident you want to be? I mean, well, okay, let's be within reason. How confident do you want to be? You want to be, no, how confident do you really want to be in your gut? 100. You can't be 100, right? So you probably want to go with as high a confidence as you possibly can. 95 is generally used. Is anybody sitting there wondering, why the hell they use it 95? Why not use 99.9999999? It's an excellent question. You have an entire project devoted to answering it. Because there's two ways to be wrong. False positive, false negative. If you increase your confidence, you decrease what's called your power. Remember I mentioned power earlier today? Yeah, they're inversely proportional, unfortunately, mathematically. So 95%, good. That shouldn't make any sense right now. Like, why would that be? That doesn't make any sense. It's okay. We're going to develop that idea throughout the course too. 95% is generally a good starting point. Okay? Then you have to say, how much error am I willing to accept? How much of a plus or minus am I willing to accept on my poll, right? What's my maximum allowable percentage margin of error? What do you think? Can you live with 2%? Can you live with 4%? Can you live with 1%? 6%? You have to pick that before you start. You have to pick it. Now that's the worst it's going to be. That's the worst. It could be better, but that's the worst it's going to be. So you have to decide both of these things before you start. I'll tell you this right now. By default, what I see most studies do in research journals, they generally decide this to be 95%, and they generally decide this to be 3%. And that's back to Rory's question about the difference between the confidence and the measure itself. Those are the two things. That's why they live in two different spots. Yeah, that's back to your question. It's an awesome question, dude. So, how do we decide? Can we do a tiny bit of algebra? Is that okay? Tiny bit. And I've got a video to go with this one, because the video takes it further if you're interested in the calculation. But you already know the formula that we have to use. It went by kind of quickly yesterday with the penny spins. But there's a margin of error calculation, right? That margin of error calculation, margin of error, is equal to that z-score times root p hat q hat over n. Now if you look at that calculation, all these things are in it, aren't they? Confidence. That's governed by this little guy right here. 95% confidence means that guy's equal to 2. 68 means that guy's equal to 1. 99.99 means that guy's equal to like 3.5 or something like that. So that's governed there. Margin of error, right there. Sample size, we're looking for him, aren't we? Can we solve this for n? Can we solve this thing for n? Hell yeah, we can! A little tiny bit out. Let's do it together. It's going to be kind of quick. Not because I don't love algebra, but because I've got a very detailed video that walks you through this calculation. There's a couple assumptions I'm going to make in line that you might not like right now, especially being towards the end of class, might be getting hungry, low glycemic index maybe, might not be palatable. But I'm going to go ahead, we're going to solve this. So we're going to solve this together. What would you do, algebra? Do you want to do like a call and release, or call and response? What would you do first to solve this?
Square.
Oh good, square both sides! Love it, you guys are into this. Excellent, maybe you're just partially into it. Square both sides, that becomes margin of error squared, yes? Margin of error gets squared, so does the z. This thing, the radical goes away. So you got p hat q hat over n. Love it! Next, please.
Divide both sides by z.
I would. How about divide both sides by z squared, move that over here? By the way, I'll never test you on this on a test, how to do this math. This is algebra, math 65. I wouldn't do that to you guys. Margin of error squared over z squared equals this. This is gorgeous. What's next? Can I show you a really cool trick that everybody forgets from Algebra 1? What kind of equation is that? Do you remember what it's called? David's like, okay, I know it. I know it's a fraction equals a fraction. And that's called something in algebra class. Starts with a P. Ends with proportion. It's a proportion! Sorry. It's a proportion. Proportions are some of my favorite equations because there's all kinds of properties that apply to proportions. One of them, this is for similar triangles in 105. You can take both sides and just flip them because they're equivalent. If 1/2 equals 1/2, then 2/1 equals 2/1. So algebraically, you can just flip these things and have z squared over e squared equals n over p hat q hat. That's totally legit. I mean, you can do it long ways too by multiplying by n, multiplying by z squared, and dividing, but you get to the same place.
So that's what we're doing?
Well, it's legit to do that.
Okay.
And we're trying to get n solved for, right? The point is to get n by itself on one side. We're almost there, aren't we? All we gotta do now is move him over to this side, yes? So let's do that. So we're gonna have p hat q hat times z squared e squared equals n. Now that's your sample size. Now there's one problem you might notice about that. It's a chicken-egg problem. Can anybody see the chicken-egg problem? Why are you calculating a sample size? When do you calculate a sample size? Before you take it, right? You have to know what the sample size is before you take the sample, because the sample size is going to tell you how large a sample to have to do a study. What's the point of the study again? What are you trying to estimate? Some of the population, right? And you get, well, the margin of error, exactly. So you're trying to estimate p hat via your sample. But the problem is p hat is in this calculation, isn't it? That's a chicken-egg problem, isn't it? That's a chicken-egg problem. You're trying to estimate p hat. How big a sample do you need to estimate p hat? You need p hat to estimate p hat. That's a chicken-egg problem. Stat books ignore the obvious solution for this. You assume p hat will make your sample size as large as possible. This is why I made a video to accompany this, and I'll show you where it is on the website. You assume to make the sample as large as possible to minimize error, you assume that p hat equals 50%. That will make the largest possible margin of error mathematically. So in other words, if p hat equals 50%, so does q hat, which means this formula reduces to just this, 0.25 times z squared, all divided by the margin of error squared. That makes me happy as a statistician, because the only two things you have to pick are the confidence and the margin, and there they are, the confidence and the margin. Now, I don't expect you to be sitting here at 10 o'clock in the morning on a Thursday, right before you're going to go maybe get lunch or late breakfast, maybe some more coffee. I don't expect you to believe this, and why that makes the margin as large as possible. I made a video where I derived this formula, and I also explained to you why that makes the margin as large as possible. If you care, you might not care. You might simply take my word for it. That's okay too. I appreciate your confidence in me. Not this confidence. If you want to see why, on the extra resources page there are 2 justification videos. In one of them I derived this formula right here from yesterday, from Tuesday. In the other I re-derived this with a neat Algebra 2 kind of explanation as to why 0.5 does that. It's a worst case scenario. It's a worst case scenario. At worst, p hat equaling 0.5 will make the largest possible margin. Now hopefully you understand why just looking at this formula. If you don't, if it's been too long since algebra, that's what I assume. That's why I made the video. So take 10 minutes and watch that, get a kick out of it. Maybe you get something out of it. Maybe you don't, maybe you trust me, that's fine too. Next time, because we're just about out of time, I gave some of you in 243 a program called SSZ Calc. SSZE Calc, I'll show you to you real quick up here. If you don't have it, we'll break a little bit early today and I'll give it to those of you who don't have it. Let me show you what it looks like.